Welcome to the final video in our series on analysis of variance. In this video, we will use our ANOVA simulator to deepen your understanding of the concepts we've presented in our previous lessons. If you haven't watched our earlier videos, you might find it beneficial to do so, as today's lesson builds on many of the concepts presented in them. We'll begin by introducing you to the capabilities of our ANOVA simulator. After that, we'll use the simulator to demonstrate how the results of ANOVA can vary when analyzing different data sets. Using a simulator like this can make complex ideas more tangible, which we hope will provide you with a richer understanding of analysis of variance. So let's begin. Here are the details about how our ANOVA simulator works. There are 9,000 scores built into the simulator, which have been divided into 3 groups of 3,000 scores each. These scores will serve as the populations from which samples will be drawn. The scores in the populations are normally distributed. We can set the following population parameters to any values we wish: the means, the variance, the sample size, and the alpha level, which will be used for our ANOVAs. After we set the parameters for the population, each individual score in the population is built using the elements of the factor model for individual scores. We do this by computing a grand mean, a treatment effect, and an error score for each person. The grand mean is the average of all the scores in the populations. The treatment effects for each group are the differences between the group mean and the grand mean. The error score is created by using a group of 9,000 random numbers with a mean of 0 and a standard deviation of 1. These error scores are first scaled to reflect the population variance, and then one error value is added to each individual score to simulate random error. The error scores in the simulated populations will always have a mean of 0 and a variance equal to the variance that we set in the simulator. If you want more information about the factor model of individual scores, we have produced a video simulation and discussion on the topic in another video in this series. Once we have the population parameters set, we can take samples from the populations and compute an ANOVA on them. Now that you know a little bit about how our simulator works, we will move on to the simulations. We will be conducting a total of 5 simulations in this video. The first 4 simulations will demonstrate an analysis of variance performed on random samples drawn from our simulated populations. We will then interpret the results of each. Because we are running simulations, we will also be able to see whether the conclusions we draw from the analyses are consistent with the true population values which will be known to us. In the 5th simulation, we will run 500 ANOVAs on samples drawn from the same population to see how closely the average results from the statistics we calculate match their long-run expected values. Here is our first simulation. Here are the settings for our first simulation. We will begin by setting all the population means to 100. The variance of all the populations will be set to 225. By doing that, we ensure that the assumption of homogeneity of variance is met. The sample sizes are set to 30, and the alpha level for the ANOVA is set to 0.05. Once we enter that data into the simulator, the first group of samples are randomly selected from our populations. Let's start by looking at the means of those samples. The means of our 3 random samples of size 30 were 99.97, 96.38, and 98.64. Notice how they differ from the population mean of 100. In a real ANOVA, the question that we would be interested in is whether the differences in these sample means were due to the effects of our experimental treatment or simply to sampling error. However, because we are running a simulation, we already know the answer to this question. All the population means have been set to be equal to 100. This can be confirmed by looking at the section of the simulator that calculates the population means from all the samples to see that the means of the populations are equal to 100, as we set them to be. So, the differences between the sample means must be due to sampling error. We can also look at the variances of each of the samples. We know that the actual variances of the population scores were set to 225, but the variances of the samples were 244.93, 222.29, and 156.94, all of which are different from the actual population variances. So we know that these differences must have been due to sampling error as well. We also know that even though the sample variances were not equal to each other, the assumption of homogeneity of variance has not been violated because in the population, the variances were set to be equal. We can confirm that by looking at the section of the simulator that calculates the variances of the 3,000 scores in each population to see that they are set as expected. Now we will examine the ANOVA summary table, which contains the results of the analysis of variance that was computed on our sample data. The first thing that we can confirm is that, as expected, the total sum of squares equals the sum of the within-group sum of squares and the between-group sum of squares. In our simulation, the within-group sum of squares is 18,100.55, and the between-group sum of squares is 198.49. The total sum of squares is therefore 18,299.04 as expected. Therefore, all the variability in the data is accounted for, either within groups or between them. Next, we can look at the mean squares and the degrees of freedom for each. These values represent the average variability within and between the groups, respectively. The within groups mean square is 208.05, and the between groups mean square is 99.25. These values are equal to their respective sum of squares divided by their degrees of freedom. You can also see that the between groups degrees of freedom equals 2, which is the number of groups minus 1, and the within groups degrees of freedom is 87, which is the total number of observations minus the number of groups. We can now move on to a discussion of how we draw a conclusion about the meaning of these data. We'll start by discussing the observed F ratio. This is our test statistic in ANOVA. It's calculated as between groups mean square divided by within groups mean square. For this simulation, F obtained is 0.48. As you have learned, the numerator for the ratio is the between groups mean square, and the denominator is the within groups mean square. The between groups mean square is a measure of both the variance of the sample means and the variance due to random error. The within groups mean square is a measure of only random error. When the null hypothesis is true, as it is in this case, both the between groups mean square and the within groups mean square are both an estimate of the same quantity, the true population variance. Because they both are estimates of the same value, their ratio should be equal to 1 if the null hypothesis that there are no differences between the population means is true. But in this case, the F ratio is actually less than 1, even though we know that the population means are equal to each other. In the population, the between groups mean square can never be less than the within groups mean square. It will either be exactly equal to the within groups mean square, if the null hypothesis is true, or larger than the within groups mean square if the null hypothesis is false. The fact that the F ratio is less than 1 in this example is another good example of sampling error at work. The mean squares are calculated from the sample values, which are subject to sampling error, so the results of any calculation done using those values will be affected by sampling error as well. This is what accounts for the fact that in this example, the between groups mean square is less than the within groups mean square. Now we can interpret our F ratio and draw conclusions. We have set our alpha level at 0.05. The F critical value for samples with 287 degrees of freedom and an alpha level of 0.05 is 3.10. Our F ratio was 0.48, which is much less than the F critical value. The probability of obtaining an F ratio this small, if the null hypothesis that the means in the population are equal to each other, is very high. This is shown by the p-value of 0.622. This means there's a 62.2% chance of observing such an F statistic if the group means were truly the same. Since this p-value is quite high and our F obtained is less than the critical F value of 3.10, we fail to reject the null hypothesis when the alpha level is set at 0.05. The bottom line in this simulation is that the results of our ANOVA enabled us to draw the correct inference that the means of the populations were equal to each other. Because we are running a simulation and we know what the true population means were, we also know that this was the objectively correct decision. We will now draw a second set of samples using the same population settings as we used in the first simulation. The population means are all set to 100, the variance is set to 225, the sample sizes are 30, and the alpha level is 0.05. Let's start by looking at the means of the new samples. The means of our three random samples of size 30 are 101.27, 99.98, 113.12. As before, notice how they differ from the population means of 100. Because all the population means have been set to be equal to 100, the differences between them and the sample means must be due to sampling error. The same would be true of the sample variances. Any differences between them and the population variance of 225 must also be due to sampling error. Now we will examine the ANOVA summary table, which contains the results of the analysis of variance that was computed on our sample data. You can review the sum of squares, the mean squares, and degrees of freedom in the table, but their analysis is the same as we discussed in the first simulation, so we will not repeat it here. Instead, we will move directly to a discussion of the results of the ANOVA. We have set our alpha level at 0.05. The F critical value for samples with 2 and 87 degrees of freedom and an alpha level of 0.05 is again 3.10. The F ratio from the ANOVA is 7.33, which clearly exceeds the F critical value of 3.10. The resulting p-value is 0.001, suggesting a very slim 0.1% likelihood of obtaining such an F ratio if the group means were truly equivalent. Given this small p-value and the F ratio that surpassed the critical F value of 3.10, we would reject the null hypothesis that the means are the same in the population in favor of the alternative hypothesis that at least one of the means are different from the others. However, because we are running a simulation, we know unequivocally, due to the simulation settings, that the population means are actually identical. The null hypothesis is, in fact, true and shouldn't have been rejected. What we're seeing here is a type 1 error in action. Often termed an alpha error, it's a false positive. This means we're detecting differences in the sample means when there aren't any differences among the means in the population. While statistical tests, including ANOVA, provide powerful tools to make informed decisions, they're not infallible. There's always a probability, however small, that we could arrive at an incorrect conclusion. This is why the significance level, or alpha, is crucial. It represents the probability of making a type 1 error. In our case, the alpha level was set at 0.05 or 5%, which means there's a 5% chance of incorrectly rejecting the null hypothesis when it's true, and in this simulation, we've landed in that 5%. If we ran the same study with different samples 100 times, we would make an alpha error like this approximately 5 times. We are going to demonstrate this via simulation a little later in this video. For our third simulation, we are going to set the population means to 95, 100, and 105. The other population parameters will be kept at the same values as in the other two simulations. The variance is set to 225, the sample sizes are 30, and the alpha level is 0.05. As before, we will start by looking at random samples drawn from these new populations. The means of these three random samples of size 30 are 93.24, 101.2, and 106.53. As expected, these values differ from the means of the populations from which they were drawn due to sampling error. The same is true for the sample variances. Now we will examine the ANOVA summary table, which contains the results of the analysis of variance that was computed on our sample data. Again, you can review the sum of squares, the mean squares, and degrees of freedom in the table, but their analysis is the same as we discussed in the first simulation, so we will not repeat it here. Instead, we will move directly to a discussion of the results of the ANOVA. We have set our alpha level at 0.05. The F critical value for samples with 2 and 87 degrees of freedom and an alpha level of 0.05 is still 3.10 because the between group and within group degrees of freedom have not changed from our previous simulations. For this analysis, the F ratio is 7.95. This exceeds the F critical value of 3.1. The p-value associated with the F ratio of 7.95 is 0.001. The likelihood of observing such a large F ratio if the means of the populations were actually equal to each other is very small at 0.1%. Therefore, the ANOVA results indicate that we should reject the null hypothesis in favor of the alternative hypothesis that at least one of the population means is not equal to the others. Because we are running a simulation, We know that the population means are indeed not equal to each other because we set them to be 95, 100, and 105 to begin with. Therefore, we can see that the ANOVA resulted in a correct conclusion that the null hypothesis should be rejected. For our fourth simulation, we are going to keep the population means at 95, 100, and 105. The other population parameters will be kept at the same values as in the other three simulations. The variance is set to 225, the sample sizes are 30, and the alpha level is 0.05. As before, we will start by looking at random samples drawn from each of these populations. The means of the three random samples of size 30 that the simulation produced are 96.77, 99.87, and 101.18. As expected, these values differ from the means of the populations from which they were drawn due to sampling error. The same is true for the sample variances. We will now discuss the results of this ANOVA. We have set our alpha level at 0.05. The F critical value for samples with 2 and 87 degrees of freedom and an alpha level of 0.05 is still 3.10. In this analysis, the F ratio is 0.75. This is lower than the F critical value of 3.1. The p-value associated with the F ratio of 0.75 is 0.476. This indicates that there is a substantial probability of observing an F statistic of this size if the group means are identical. The conclusion that we would draw from these data is that it is most likely that the means of the population are equal to each other. Therefore, we would fail to reject the null hypothesis that at least one of the means is different from the others. However, this conclusion would be incorrect. Failing to reject the null hypothesis is making the statement that it is most likely that all the population means are the same. Remember, in this simulation we expressly set them to be different from each other, with values of 95, 100, and 105. So if we fail to reject the null hypothesis, this would be an error. In statistical terms, this is known as a type 2 error, or a beta error. It's the opposite of a type 1 error. While a type 1 error is about seeing an effect that isn't there, a type 2 error is about missing an effect that really is present. In this case, we would say that our test did not have enough power to detect the fact that the population means are actually different from each other, in part because the differences in the sample means were quite small. While we haven't covered a type 2 error in this series of videos, you may already be familiar with it from your statistics course. So we thought that it would be important to at least mention it as it is a critical type of error that you can encounter when running an ANOVA. In our final simulation, we are going to demonstrate some concepts that can only be examined using a simulator. They are the expected values of an ANOVA. In our videos on ANOVA, we discussed what the expected value of the between groups and within groups mean square were when the null hypothesis was true and when it wasn't. You learned that when the null hypothesis was true, both the between groups and within groups mean square were an unbiased estimate of the population variance. So one should expect that the mean squares would be equal to each other when the null hypothesis was true. However, you saw in our previous simulations where we set the population means equal to each other, that the between groups mean square and the within groups mean square were not actually equal to each other when we ran an ANOVA, due to the expected effect of sampling error. In addition, when the null hypothesis is true, the F ratio, which is defined as the between groups mean square divided by the within groups mean square, should be equal to 1. This was not true in the ANOVAs we ran and was also attributable to sampling error. We are now going to run 500 ANOVAs and record the between groups mean square, the within groups mean square, the F ratios, and whether the results of each ANOVA were significant. We are then going to average those values over all 500 runs and compare the results to what we would theoretically expect them to be. By doing this, we can approximate the expected values of those quantities. As you have learned, this would only be an approximation of the expected values, because in order to find the true expected value, we would have to run an infinite number of ANOVAs. For this simulation, we will set all the population means to 100, the variance to 225, the sample size to 30, and the alpha level to 0.05. We will now start the simulation. As you can see from the iteration counter, the simulator is now running 500 ANOVAs, taking a new random sample from our population for each run. While it is running, let's discuss what we might expect to see. We have set the population variance for all the groups to 225. Because we set the population means to be equal to each other, in the population, the only source of variation in the data should be this error variance. Just as the means of the samples are estimates of the population means, the variation in each of the samples is an estimate of the population variance. As with the means, sampling error is the reason why the variance of the samples is different from the population variance that we set. You have learned that sampling error is a random phenomenon. So, over repeated samplings, the effect of sampling error will be 0 if the samples are randomly selected. Because of this, over the 500 iterations, the sampling error present in the sample variances should approximately cancel itself out, and the average variance of the samples will be close to the population variance. Because we have set the population means to be equal to each other, the only source of variation remaining in the data is the population error variance, which we set to be 225. Since the between groups mean squares and the within group mean squares are both estimates of the population error variance when the group means are equal, we would expect the value of both of them to be close to 225. Here are the results from the 500 simulations. The average between groups mean square was 238.83, and the average within groups mean square was 225.74. Given that the population means were all set to 100, the expected value of the between groups mean square and the within groups mean square would both be 225, reflecting the fact that the only variance in the data should be due to error variance with no variation due to treatment effect. As we pointed out, the individual between groups and within groups mean square values obtained from each individual ANOVA can exhibit a wide range of variation due to sampling error. You can clearly see this when you look at the results of the individual ANOVAs. However, when these results are averaged over 500 simulations, the between groups mean square and within groups mean square values have converged close to their expected values. Regarding the F ratio, the average value across the 500 simulations was 1.09. This is very close to what we would expect if the between groups mean square and the within groups mean square were equal to each other as they are in the population used for this simulation. An F ratio close to 1 is consistent with what one would expect when there are no differences between the means of the groups. It's worth noting that even when there are no differences between the means and the population, individual F ratios will exhibit substantial variation, as evident in the results of the individual ANOVAs. Finally, let's look at the frequency of type 1 errors. Out of the 500 simulations, there were 32 instances where a type 1 error occurred, resulting in an error rate of 6.4%. This means that 6.4% of the time, we would have incorrectly decided to reject the null hypothesis based on the outcome of the ANOVA. Given an alpha level of 0.05, the expected type 1 error rate is 5%, or 25 errors out of 500. As you can see, the observed rate is very close to the expected rate. If we had run an infinite number of iterations, we would have found that the type 1 error rate would have been exactly 5%. This concludes our video demonstrating analysis of variance using simulations. It is also our last video in our series on one-way between subjects ANOVA. In case you haven't seen them, the other videos in this series covered variance, random sampling, the central limit theorem, experimental error, the factor model of individual scores, and basic concepts of analysis of variance parts 1 and 2. We hope you have found them all to be valuable additions to your classroom study of ANOVA. Thank you for watching.